Let's look at one more problem, example problem in today's session, which really doesn't have anything to do with the primary topic today, which was rotational energies and rotational partition functions. This one really has more to do with excited states of an electronic partition function, which we really haven't gone over, but we don't need to do much on it. So let's take a look at this problem. We have more than enough background to attack it. This one has is of some interest to people who are astrophysicists. Uh, and the question is the average kinetic energy of hydrogen atoms in a stellar gas or in a star is 1 electron volt. What is the ratio of the number of hydrogen atoms in the second excited state to the number in the ground number in the ground state? And we just have to remember a few things from your previous classes. The energy levels of the hydrogen atom are minus 13.6 electron volts over n squared, where n is the principal quantum number, and it starts with 1, 2, 3, etc. And you have to remember that. I assume that you've seen that one or two of your chemistry classes. And you also need to know the degeneracy of each one of those levels, which if you don't remember that, you can look it up, but I'll just give it to you. It's 2 times the principal quantum number n squared is the degeneracy of the levels. This is assuming some things like the Pauli exclusion principle and some other factors for atomic orbitals. And what we're asked is the number of particles in the second excited state, the ratio with that to the ground state. So we're asked n3. Remember, second excited state. The first excited state is n equal to 2. The ground state is n equal to 1, and so the second excited state is 3. So I represented the number of particles in that level as n3 to the ratio of the number of particles in this gas in the ground state. And then really we just have to understand that this factor here over z, g times the Boltzmann factor divided by the partition function, is the probability. And if there's a total of n particles in the system, then the probability times n is just the number in the energy level E3, for instance. And likewise on the bottom. The thing that's kind of neat about it is I don't ever have to calculate the partition function for this electronic system of hydrogen gas. I know everything here now. The z's cancel, and I simply have put in the degeneracies for the upper level. For the third level, it's 2 times 3 squared. For the lower level, the degeneracy is 2 times 1 squared, which is 2, so you can put 2 electrons in the ground state, and so on. And then the energy levels, I actually know those as well too. I just left them here, but I wrote this as a single exponent. And I think if you flip this over on top, it becomes positive, and then I include them both inside that exponential. Now then, we use the other piece of information to get what the temperature is effectively. We're given up here that the average kinetic energy, so this is translational kinetic energy, is 1 electron volt. And we've seen earlier that that's given by 3/2 kBT is the expectation, or the average kinetic energy, treating the stellar gas as an ideal gas. Here. And I can actually solve this for the temperature. It takes a little bit of unit conversion, but I don't really have to do that here. I can just set this equal to, since we're given that the average kinetic energy of one of the particles in the gas is 3/2 kBT is 1 eV. I can just solve for the kB times the temperature and just divide through by 2 by 2/3 to bring this over to this side. And so whatever the temperature is, when I multiply it times KB, I get 2/3 an electron volt by the hypothesis in this problem anyway. And that's really all that I have to have on this. I can plug in the energy level of the second excited state. It's minus 13.6 eV over n squared, 3 squared. Subtract from it E1, which is 13.6 divided by 1 squared. That's the ground state energy. And then the KBT, I just leave it as 2/3 EV, electron volts. That's the product of those two. And if you look at that, the electron volts in the denominator here will cancel these two in the numerator. I have minus and minus is a plus, so I wrote this one here. And when I divided 9 into 13.6, I got 1.51 electron volts here. The EVs cancel, as I stated. And then I just have a pure number up here, which I have to have because it's an argument of a function. And when I computed that, I got minus 18.1. The degeneracy factors, G3 over G1. When I compute those, 2 times 3 squared is 9, and 2 times 9 is 18, and on the bottom 2. And of course 2 goes into to 18 9 times, or probably been easier to just cancel these two 2's, and it just simply becomes 3 squared divided by 1 squared, and 3 squared is simply 9. Okay? But I get this factor, and when I computed that, I got 1.2 times 10 to the minus 7. And so that's the ratio of the expected number of particles in the second excited state to the ground state. And you see it's a very small number for this stellar, treating it as an ideal gas for stellar gas. You might ask, well, what is the temperature associated with this value up here? I didn't really solve for it, but I know that KBT is equal to 2/3 EV. So just for reference, let's compute that. I think I did that next. Yes, I did. So I use that relation that I have, and so I can solve this as 2/3 electron volt and divided by Boltzmann's constant. So I have the 2/3 EV, 1 over Boltzmann's constant. Now I just need to convert some energy. I know that there's 1.6 times 10 to the minus 19th joules in 1 EV. So the EVs cancel, the joules cancel, the Kelvin flip over on top. And when I multiplied 2/3 times 1.6 times 10 to the minus 19th and divided by 1.38 times 10 to the minus 23, I get a little over 7,700 Kelvin. And that's pretty typical of stellar gas temperatures. So it's kind of surprising because even at this high of a temperature here, very high temperature, the number of atoms that are in the second excited state to the ground state is still a very small fraction. So even at elevated temperatures, most of the atoms are in the ground of these hydrogen gases is going to be in the ground state.